Swayam Prabha. Digital India. Educated India.
We are in our C401 Water Resources Engineering. We are looking the very important hydrological processes, that is runoff. And the last class we have seen what is runoff, how it is measured, and how to make the time series of a runoff. When we make the time series of runoff, depending upon the volume of water flowing in the stream, the rivers can be classified. But before that, over the period of the time, people have observed that there is a persistent in the occurrence of rainfall duration, right? And depending upon that persistent as well as the wind from in which direction it is coming, the monsoon, the group of days, raining days are classified as monsoon. So depending upon from which direction the air is blowing or the clouds are coming from which direction, the monsoon are majorly classified as southwest monsoon. That is the first monsoon entering into India that we have seen during precipitation, right, which starts in the month of June 1st, right. The second type of monsoon is northeast monsoon. So what happened, this southwest monsoon is the monsoon which brings copious amount of rainfall throughout the country. So then what happens, prior to this southwest monsoon, there is a summer. So no agricultural operations can start without surface water or without rain. So then what happens, people are starting their agricultural operation once there is an onset of southwest monsoon. So in India, the water year starts from 1st June to next year 31st of the calendar year. Similarly, the irrigation monsoon also, right? The first southwest monsoon is called as Kharif period and then followed by Rabi season. Right? These two are depending upon the type of reservoir operation, you will get water for two monsoons, that is Kharif and Rabi. And this time period of June 1st to May 31st is called as water year. Okay, why this water year? Because we do all water budgeting depending upon this water year as the planning period. Your model estimation of rainfall may be for every day or every 10 daily or every weekly, every monthly, every season, but planning period is 1 year and the starting period is June 1st to 31st. Similarly for reservoir operations. So within this 1 year, right, from June 1st to May 31st, how the discharge time series looks like in a stream, right? If there is a continuous rainfall, so depending upon that we have three different types of streams. When there is a continuous rainfall, even during summer, and this is January to December, so from June month it starts rising. So that means this is southwest monsoon and northeast monsoon. Then after December it goes on reducing and reaches the minimum value during the month of April and May. But still the discharge is more than zero. So such streams are called as perennial streams. The monsoon flow is due to rainfall in the catchment area, and this summer flow may be due to the groundwater flow or may be due to snow flow. In Ganges, Brahmaputra, the flow are due to snow melting, whereas in Deccan and the southern rivers, the perennial river system is due to groundwater flow. Intermittent system is irrespective of its location, the flow during summer period is zero. That means there is no either groundwater contribution or snow melt contribution. Totally the dry bed is dry or river bed is dry. And such a monsoon which has flow only, continuous flow only during monsoon period is called as intermittent rivers or intermittent streams. Reservoirs located on such rivers are called intermittent reservoirs. Right? The third type is ephemeral stream. That means whenever there is a rainfall, there will be runoff. Even there is no delayed runoff also. Such streams are called as ephemeral stream. Okay. So these are all three types of streams which we come across. Similarly, depending upon the groundwater flow, the stream can be called as effluent stream. That means a stream which receives water from the groundwater is called as effluent streams. A stream which contributes to groundwater is called as influent streams. This is from groundwater level, groundwater viewpoint. Now we will see this, why it is happening like this. What are all the characteristics which governs this um, flow in the river basin, right? Now we can see broadly classify the factors which governs our stream flow or the flow characteristics of a stream depends upon three important characteristics. One is the rainfall characteristics, second one is catchment characteristics, third is climatic factors. Right? See, rainfall is also climatic factor, but major rainfall. So there are three important characteristics of rainfall which governs the stream flow. First one is magnitude, that means centimeter per hour, right? Intensity. The second one is distribution time, how far the rain has happened, right? Space and its variability, whether it is happening uniformly over the entire catchment or in one location it is heavy intensity rainfall, in another place there is no zero. So these are all the governing factor of rainfall which governs the flow characteristics. Second is the catchment characteristics, right? Apart from what we have seen in the fourth chapter, catchment characteristics, the type of soil, vegetation, type of vegetation, thickness of vegetation, canopy cover, all these things comes under vegetation type. And also the slope of the basin, geology and shape, drainage density. These are all the catchment characteristics which governs the flow characteristics. Finally, the climatic factor, evapotranspiration. Suppose if there is a thick forest and huge quantity of water is lost through natural evapotranspiration, so that is called natural evapotranspiration, then your runoff will be very less. So we will see this one by one. Alright. So I have just relisted everything as climatic factors and physiographic factors. Some books give it as 3, 4, 5 characteristics. I have broadly classified this into two. One is climatic factor, another one is catchment characteristics, right? So in climatic factors, everything comes: rainfall, intensity, duration, distribution, right? Direction of the storm movement. Suppose if the storm, that means the cloud, moves from the measurement point towards the starting of the mountain, then you will have rainfall, immediately heavy runoff, and then slowly it goes down. But if it is happening, the storm is moving from the mountain to the measurement point, slowly the runoff will increase. It reaches the peak, and once it crosses, it goes down. Right? Similarly, the antecedent precipitation. That means it tells about what is the soil type, soil condition before the current rainfall. Then other climatic factors, evaporation, transpiration, right, relative humidity, wind speed, evapotranspiration, all this governs the runoff. When we come to this catchment characteristics, whatever we have seen, land use, land cover, soil type, area of the basin, shape of the basin, elevation, slope, orientation, right, type of drainage network, right. This orientation is also very important. Orientation is, that is why whenever you read about a river, they will say that the river after originating from this so and so place flows towards east direction and then takes a 90-degree turn and then flows towards south and then takes another 90-degree, moves, joins with a particular sea or ocean. Because as I said, there are only two predominant wind direction, southwest and northeast. Suppose if the southwest if the river is oriented towards northeast to southwest, that means my entire clouds will be moving over the entire basin. Then I will have more rainfall, right? Like what happens on the west side of Western Ghats. That's why during southwest monsoon we have heavy rainfall on the Western Ghats, because the rainfall, the clouds covers the entire basin. And if my basin is oriented towards on the opposite direction of my wind flow, then we'll have less runoff. So this is how the factors affects, right? Now we will see what is annual runoff. Sometimes the annual runoff volume is also called as yield of the basin. Sometimes this yield is after all losses, right? So the total quantity of water that can be expected from a stream in a given period is called as yield of the basin, right? This is what, when you go to the field, they will not say runoff, they will say that yield of the basin, because the storages in the basin are estimated based on this yield, 75% of the yield, or 75% dependable yield, or 90% dependable yield. This is how we store the water, because the calculation of this yield is the fundamental importance in all water resources studies, because this is what the volume of water you are going to store. It is not the total runoff available from the basin, right? So that is why I am very particular in telling you the water yield of a watershed is the amount of fresh water generated from a combination of base flow, interflow or overland flow originating from groundwater or precipitation and or snowpack. Altogether it is the total water available for human use, right? So the first way is to measure it. That is what we have done. If it is not possible to measure, then we try to estimate, right? There are 2-3 methods to estimate. Now we have several methods, right? But all are clubbed into these 3 methods. The first one is empirical equations, right? I think you know what is an empirical equation. That means I do some experiment. I have collected certain amount of input and certain amount of output and try to develop a mathematical equation. Need not be a linear equation, maybe any other non-linear equations also. The equations in which the left hand side and right hand side are dimensionally non-homogeneous, such an equations are called as empirical equations. If they are dimensionally homogeneous, left hand side quantity and right hand side quantity, we call it as a rational equations, right? That is first method of estimating the yield. The second one is correlation study between the observed stream flow and observed rainfall. Or nowadays we are using this watershed simulations, right? Like our physical model, conceptual model, right? Data mining techniques, or sometimes we use this finite difference, finite element, all comes under this watershed simulations. Let us see one by one, right? Before that, I would like to tell what is this dependable yield, right? Is the so dependable yield, right, is the annual yield from a basin, right, and is the effect of various other process. They are all random, but we call that as a stochastic process, right? And this magnitude varies from year to year. The yield from a basin is not constant. It depends upon the rainfall and antecedent soil moisture condition of our basin, as well as the basin characteristics. And it varies from year to year. If you see the annual rainfall in the basin, average annual rainfall and average yield, some years same rainfall but yield will be different, right? They are all other basin characteristics also governs, right? So the annual yield in any year in future can be estimated with some degree of dependability, right? That means with the observed data, you estimate its probability of occurrence and then use that values to estimate the future yield. Thus, for example, 75% dependable yield in a basin is the annual runoff volume of the basin which can be expected or equaled or exceeded on the average 3 years out of 4 years. Right? If I say that my reservoir has a capacity of 75% dependable yield, that means if I operate for 4 years, 3 years, the reservoir capacity should be more. But this 4 years is the total cycle, which is not correct. For example, in our case, it is 60 years. 75% of the 60 years, so how much? 45 years, your reservoir will be having a good inflow. That's the meaning. Here, the 75% dependable yield volume will be less than thus 50% dependable yield, because 50% of the year, if my dam has to be filled, the volume will be large. Okay, we will see that one by one. And this is estimated using your frequency analysis, which you have done for your rainfall using your empirical probability distribution methods for the observed data. Right? Let us assume we'll do an example problem. Everybody can take a pen and paper. Right? See, it says that the annual yield of a basin in million meter cube observed for a period of 19 years, right? Or 832, 672, 488 and so on, right? 19 data points. Using the frequency analysis, determine 75% dependable yield, 50% dependable yield, and also find what is the dependability of the yield for 1300 million meter cube. 3 questions, right? So first what you have to do, first you put it in year wise, right? This is my observed data for 19 years. Then what is the first step in fitting the probability? You list down the data with the descending order, in descending order. The highest value, lowest, then low, and the minimum most value will be at the bottom. Now you write down what is the rank. As I previously explained, rank is nothing but how many times this quantity and more than this has occurred within this observed period. For example, I am putting 1, 2, 3, 4. No? Let us take this 4. The probability of the rank for 984 magnitude of yield is 4. That means what? This quantity 984 has occurred 4 times in the observed data. Need not be continuous 4 or first and last. Altogether in the observed data of 19 years, 4 times a quantity of 984 and more. Right? So once I give the rank, earlier I said when it is equal, you consider any one. Right? Now first is exceedance probability. That is rank by n plus 1. M by n plus 1. M is the rank, n is the number of data point. So m by n plus 1. So what method it is? Sweebull's method. Right? So I am estimating the probability of exceedance. The inverse of this probability of exceedance gives me the return period. Okay. Now, what to do with this? How I can find 75% dependability? The exceedance probability is nothing but the 70% dependable yield. So you can draw a graph between the annual yield in x-axis and exceedance probability in y-axis. Right? For 75%, if it is some data points, right? If it is 30 years or depending upon this exactly 0.75 may not be there. Then we have to linearly interpolate between the two values. Then you can find out what is the 75% dependable yield. So for 0.75 means 75% dependable yield. It is 536 million meter cube. Then what is the dependable yield of 50%? It is 720 million meter cube. Suppose if the yield, the probability of yield of 1300 million meter cube is a probability of exceedance of 0.12. Okay, so this is the purpose of dependable yield estimation from the observed runoff. So you can take this as your live storage available for storing, right? 75%. You no need to store all the 530. It depends upon what is your demand. That is estimated using another method called as ripple diagram that we will see after this. Okay, so it is like estimation of supply, right? In layman, we can say that yield is nothing but the supply from the basin every year. With the 70% dependable is 536, 50% dependable is 720. Okay. Now we will see these models in detail, how to estimate that quantity of yield. First I said empirical, we will see in detail about empirical, all other things we will try to show some examples, right? There are 4 different methods nowadays. Earlier it was only 3, now it is 4. Empirical methods, conceptual models and physically based models. Right? Empirical models are based on observational data between input and output. Conceptual models, you consider each and every process in your hydrological cycle, right? Then based on their algorithms, okay, you can put it in terms of mathematical equations. Then you will get the output. For example, derivation of instantaneous unit hydrograph, right? Nash model actually is a mathematician who got Nobel Prize for his works on derivation of this mathematical subject. And his model in derivation of instantaneous unit hydrograph is a conceptual model. No experiments, nothing. Every process is considered based on the physical process equations. Then the third method is physically based models. In this, you develop a relationship for each and every processes, right? For example, the for infiltration, you can estimate or use Harton's equation, right? That means you do some experiment, derive a particular relationship based on your experimental data, and use that equation as the equation in your water budget. Instead of writing the ground flow equation as a infiltration model. So this is physically based model. Now we have 4th model, that is called as artificial intelligence based models, right? Out of all these 4 models, empirical models are age-old techniques. When we don't have sufficient quantity of observed data, people used to develop relationship between discharge and catchment area. See, the input is area of the catchment, output is discharge. You see, area is in kilometer square, discharge is in meter cube per second. So it's an empirical relationship. Then in 1960s, 70s, from 30s to then we had physical models and conceptual models. After 95, 96, we have this artificial intelligence techniques, application of ANN model, model tree, genetic program, because our time series length was longer and longer. But each and every method has their own advantage and a disadvantage. Let us see some of the empirical equations which were developed and applied in Indian condition, right? Please remember these empirical equations are site specific. An empirical equation which is developed in one basin or one location of the basin cannot be employed to other basins, okay, unless you test it, right? So we will see some of the famous equations. The first one is Binnis percentages, right? Barlow's table, Strange table, English, and this is SCS curve number technique also started as an empirical equation. Now it has gone to physically based models. In semi-distributed models, we use this. Even distributed models, we use this SCS curve number techniques. Now we'll see one by one, right? So Binnis percentage, right? It was developed by Sir Alexander Binney, right? With here a correlation between observed runoff and the area, okay? And he gave the runoff as percentage of rainfall, okay? And this was developed for small catchments near Nagpur with the observed data from 1969 to 72. Right? So these percentages are being used in Madhya Pradesh, Vidarbha region of Maharashtra for estimation of yield, annual yield. Right? So that is Binny's percentage. The second one is Barlow's table. Barlow is the first chief engineer for Hydroelectric Survey of India. He conducted study of small catchments, area up to 1300, and he gave the first um, rational equation that rainfall is equal to a percentage and rainfall. P is for precipitation. And this runoff coefficient, he gave different values and he called that as runoff coefficient. So now you can say that runoff coefficient is the ratio of runoff by precipitation. And he also gave that this is function of type of catchment and the nature of monsoon rainfall. Right? So you can see this Barlow's coefficient. He divided the catchment into 5 A, B, C, D, E. Right? And he divided the season also. But he has not told which season it is. But it depends upon the intensity of rainfall. Season 1 is light rainfall, no heavy downpour. Season 2 is average with varying rainfall, no continuous downpour. Season 3 is continuous downpour. Please remember, please see this, don't try to memorize this number, try to understand this number. Okay, see, for there is variation from one row to another row and from one column to another column. Let us take this flat cultivated soil. For light rainfall, the runoff coefficient is very small, and for average rainfall, the runoff coefficient is slightly higher, and for good rainfall, the runoff coefficient is very high. Let us take in one season where the rainfall is very light, but depending upon the soil type, for example, flat, less. Same rainfall, if it is a hilly, steep and hardly cultivated, your runoff coefficient is 0.36. That means we, he has very nicely developed a relationship between the basin characteristics as well as rainfall characteristics. Okay, so the minimum runoff coefficient varies from 7 and maximum runoff coefficient is 81. Right, the 2-year season in hilly area you will have a 180% of your rainfall goes as runoff. Okay, this is Barlow's runoff coefficient in percentage. Right, so this can be applicable only in UP. Right, I think you can think of UP comes under which mountainous region. Then this strange table method. This strange table method developed in 1928 in southern river system. This is one I think only one method in empirical where you can develop daily rainfall, daily runoff as well as monsoon runoff. See, all other methods, that is annual yield or monsoon yield. Okay, but strange table method you can estimate daily runoff, because in strange table it is also same. He also given a runoff coefficient which is considered as ratio of runoff by precipitation, and this is estimated based on the observed daily rainfall and runoff in the border area of Maharashtra, Karnataka, Tamil Nadu and Andhra. Right? Here the strange has divided the catchments into good, average and bad catchments. Good catchment means for a given rainfall you have more runoff. Average catchment is an average relationship between rainfall and runoff. Bad catchment means it is not a catchment which does not have anything. That means the runoff is very less compared to the runoff. So runoff is very less when compared to the rainfall. That means it's a hilly forested area and you have large amount of infiltration. Right? So let us see how Strange has given runoff coefficient to calculate daily runoff from this daily data. Okay. So first we will see this monsoon, right? So the Strange table for estimation of this runoff coefficient during monsoon rainfall. The monsoon rainfall, it is similar to our Barlow's, but this is for other regions or southern region rivers. You can see the runoff coefficient depends upon the monsoon rainfall. For good catchment, it is more. For bad catchment, it is less. That means the catchment is not bad. The runoff is very less. Okay, that means the catchment is good. That means it is having holding capacity of more rainfall. The highest runoff coefficient given by Strange for monsoon rainfall is only 30%. The two with very heavy rainfall. Right? So this is for monsoon, whereas for daily data, he classified the catchment into three categories, right? Dry, damp, and wet. So already you have three catchment characteristics: good catchment, average catchment, and bad catchment. Then each and every catchment he classifies the soil moisture, antecedent soil moisture as dry, damp, and wet, depending upon the previous 5 days rainfall, right? And this is a very good, and it is available in irrigation manual published in 1932 by Anna University or College of Engineering, Gindi. So I request everyone to go through that and see how he has classified soil, antecedent soil moisture as dry, damp, and wet. So next class you can inform me. Dry, damp, wet. Okay. So, and this method is still in use, not to use it in life, but to estimate the monsoon yield. Okay, this is about Strange table method, right? Then Inglis and D'Souza formula, which is given in 1929, it looks like a linear regression equation. This was developed for Ghat regions of Western India, as well as for separately for Deccan Plateau. And English is the founder director of our CWPRS, Pune, right? Central Water Power Research Station in Pune in 1917, right? So in 2017, it has celebrated its centenary celebrations. So English and D'Souza, as named, they are from Goa region. So they have carried out the observed rainfall and observed runoff in the Ghat regions of Western India, right? So then they have developed a regression equation. This is a linear regression equation. Whereas for Deccan Plateau, this is a non-linear, right? It will come out p square minus p, right? So these equations can be used to estimate the runoff, right? But it works good, very good for annual runoff, because it is estimated using annual rainfall and annual runoff. Then Kosala's formula is used in Himalayan range. This is the only formula in our Indian condition where after that there are several equations. First equation, which considers the temperature as one of the criteria in estimating the runoff, because as the temperature increases, the runoff also increases, right? So in this case, he has given that he has considered the catchments in India as well as in US, right? Kosala's formula. So monthly runoff in centimeter, and PM is the monthly rainfall, and LM he call it as losses, right? So when the temperature is, and this he has given the condition that this equation holds good only when the temperature is more than 4.5 degrees centigrade. Then loss is 0.48 of average temperature, mean monthly temperature. If the temperature is less than 4.5 degrees centigrade, less than or equal to 4.5 degrees centigrade, then the LM is, he has given it as a coefficient. Okay, LM may be provisionally assumed, right? A constant number. in centimeter. That too now rainfall and runoff should be of rainfall centimeter units. And then you estimate for every month and you add it for the whole 12 months, you will get the annual runoff. So I have one question about this Kosala. I would like to find out where Professor Kosala has worked. So then comes empirical method, then the conceptual and physically based methods. As I said, you have to express that equations in terms of concept. Then in physically based method, you should have derived a relationship between input and output of each sub hydrological processes. That means again it depends upon the data availability. So these two methods are data intensive and they are complex and large number of parameters are involved, right? Implementation and calibration of such model can typically present various difficulties. And also these two methods require sophisticated tools. And also that is why nowadays we are using finite difference, finite element and finite volume method to derive rainfall runoff relationship using semi-distributed or fully distributed physical based models. Okay, so this is some of the disadvantages, but advantage of these conceptual and physical models are accurate estimation of runoff for a given rainfall.